Learn like a pro.
Okay, so let's talk about the invisible world all around us. I'm talking about circuit architecture. It's this hidden system of rules and pathways that powers, well, literally everything you can think of. Your phone, the lights in this room, everything. So today, we're going to break down exactly how it all works. So you look at a circuit diagram like this, and yeah, it can look like a totally complicated, messy map, right? But here's the secret to understanding it. Just forget the whole map for a second. Instead, we're just going to follow a single traveler on its journey, one single unit of charge. We're going to see where it starts, what it goes through, and where it ends up. All right, every journey needs a starting push, right? For our little unit of charge, that push comes from the battery, or what we call the source. And this boost has a fancy name, electromotive force, or EMF for short. Now, don't get hung up on the word force. It's not really a force in the way we usually think about it. It's much better to think of it as the total energy that gets packed into each unit of charge to power its entire trip around the circuit. This is basically the energy in.
Okay, so let's see what's actually happening inside that battery. Imagine our 1 coulomb of charge going in. The battery gets to work on it, converting its own chemical energy into electrical potential energy for the charge. So if a battery says it has an EMF of, say, 3.5 volts, what does that really mean? It means it's doing 3.5 joules of work for every single coulomb of charge that passes through. It's basically loading it up with a backpack full of energy for the journey ahead.
So if EMF is the energy our charge gets at the start, then potential difference, or PD, is the energy it gives up along the way. As our charge is traveling, it passes through different things, right? Like a light bulb. The PD is what measures how much energy gets handed over from the charge to that one specific component. This is our energy out.
And here we can actually see that energy transfer happening. As our fully energized charge flows through the bulb's filament, it starts to do work. It's converting its electrical energy into light and heat. You can literally think of it as an energy drop across that component. That's the potential difference. So when you see a 5-volt bulb, it just means it's designed to take 5 joules of energy from every single coulomb of charge that passes through it. Okay, so let's just boil this down to make it super clear. The key difference here is the scope. See, EMF is about the energy for the entire complete circuit, the whole trip. Potential difference, on the other hand, is just about the energy used by one specific component, like a single stop on that trip. The analogy is perfect. EMF is the total budget you have for your vacation, and PD is how much you spend on dinner one night.
But, no journey is ever perfectly smooth, right? There are always obstacles. And in a circuit, the biggest obstacle is something called resistance. Honestly, the best way to think about it is like electrical friction. As these tiny electrons try to flow through a wire, they're constantly bumping into and colliding with the much bigger ions that make up the material. It creates this atomic-level traffic jam, and that's what slows down the flow and, by the way, generates heat.
So what actually determines how bad this traffic jam gets? Well, for a simple wire, it's not random at all. It actually comes down to its physical shape. First, there's length. It's pretty intuitive, right? A longer road is just harder to travel. Well, a longer wire means more chances for an electron to collide with something, which means higher resistance. And second, there's cross-sectional area. Think of this like the width of the road. A wider wire is like adding more lanes to a highway. It just gives the electrons way more room to flow, and that decreases the overall resistance. But it's not just about the shape of the road. The road's surface itself matters, right? The material is absolutely critical. Every single material has its own built-in inherent ability to resist current. We call that resistivity. And this chart shows a fantastic comparison. You've got silver, one of the best conductors out there, with super low resistivity. And then you have iron, which puts up much more of a fight. You can think of this property as the material's unique electrical DNA.
Okay, this is where things get really interesting, because not all obstacles are just simple wires. When we start looking at actual engineered components, we find that they don't just resist current, they actively control it and shape it in their own unique ways. And if we map out how current changes with voltage for each one, we can actually see its distinct electrical signature.
First up, we've got the ohmic conductor. Think of this as the predictable rule follower of the circuit world. For something like a simple copper wire, as long as you keep the temperature steady, the relationship between voltage and current is perfectly linear. You can see it on the graph. It's a perfect straight line. You double the voltage, you get exactly double the current. Its resistance is constant. No surprises here.
But now, take a look at what happens with a classic filament lamp. The graph starts out looking like a nice straight line, but then
it curves and starts to flatten out. So what's going on? It's all about heat. As more current flows, that little filament gets incredibly hot. And when it gets hot, its internal ions start vibrating like crazy, which causes way more collisions and jacks up the resistance. The lamp is literally creating a thermal bottleneck for itself, physically choking off and limiting how much current can even flow through it. And finally, we have the semiconductor diode. Its signature is by far the most dramatic. It's basically a perfect one-way street for electricity. If you try to send current the wrong way, in the reverse direction, its resistance is practically infinite. Nothing gets through. But once you apply just a little bit of voltage in the forward direction, bam! The gate swings wide open, resistance completely plummets, and current just surges through. This little one-way gate is a fundamental building block of, well, almost all modern electronics.
Okay, so let's recap. We've got our energy source, our EMF. We've got our different components with all their unique electrical signatures. The final piece of this puzzle is deciding how we arrange them all. And really, there are two fundamental ways you can connect things. In series, which is just one after another in a single line, or in parallel, where they're side by side in different branches.
And believe me, this choice of architecture completely changes how the circuit behaves. A series circuit? That's like a single-lane country road. Every single charge has to go through every single resistor one by one. So their resistances just pile up. You just add them together. It creates the biggest traffic jam possible. But a parallel circuit, that's like a multi-lane superhighway. Here's the crazy part. By adding more paths, you're giving the current more options to flow, which actually lowers the total effective resistance of the whole circuit. More roads, less traffic.
And that brings us right back to the beginning, to the complete circuit ecosystem. When you look at it this way, it's really a perfectly balanced system. You have the source, which provides the energy, the EMF, to get the charge moving. You have the pathway itself, the wires, whose physical shape and material create the basic resistance. And then finally, you have the consumer, those special components with their unique physics that take that flow of energy and shape it to create a final output, like the light from a bulb. You know, when you think about it, every single electronic device you've ever used is just a clever combination of these exact principles: energy, resistance, and architecture, all arranged in brilliant ways. The basic rules are actually pretty simple, but what you can do with them, well, the possibilities are infinite. So now that you can see the architecture, what could you build?